Welcome back everyone. So let's continue with Deutsch-Jozsa algorithm. Okay, the recipe is going to be the same, so let's start with the review of the problem. In this problem again we are given an oracle and we are said that this oracle implements this function, which basically means that it takes a bit string or like n length bit string and it maps to either 0 or 1. We say that this function is constant if it maps all of these bit strings to 0 or 1. We say that it's balanced if it maps exactly half of these bit strings to 0 and the other half to 1, no matter the order. Okay? So, the skeleton of our code is still going to be the same. So, let's start with it. Well, in this segment, again we just import the oracle functions that we have defined and we just import the necessary modules from Qiskit, period histogram and whatnot. But for this case we need to define what n should be, the length of the bit string. I said it should be fine, 5, it's a good length. I don't know. But our quantum circuit should be one more than the length of the bit string because we also need an ancilla qubit. Alright? So we define these quantum and classical registers and we also initialize our quantum circuit using these. Okay, remember what do we need to do first? We first need to superpose all of our qubits by applying Hadamard to each of them. Alright, no problem here. Next we need to initialize our ancilla qubit to minus state, apply an X, then an Hadamard, then you're done. We put a barrier to make it look cool, nothing fancy in here. And we apply this oracle function which simulates the oracle behaviors. Again we apply a Hadamard barrier right after it, and finally we just apply a whole bunch of Hadamards and measure and interpret our results. Okay, let's see our circuit. Well, as you can see, nothing fancy, just as what we expected. Now let's run the circuit and see what does this oracle2 function do. I didn't. Oracle2 function, by the way, takes in a quantum circuit just like Oracle1, but it also needs n, like the length of our input, in order to compute it because n may vary. Okay, let's run it and see our results. Okay, what did we get? We get 10000. Well, this one is our ancilla, so don't see it. That just means that we got 000 as a result. Remember, in Deutsch-Jozsa, if you get a 000 as a result, that means that your function was constant. If you get anything other than 000 string, like full zero string, anything other than it, it just means it's balanced. Right? So what does this mean? It means it's balanced. But one thing for you to note before we move on, if I run it again, what do I get? I still get 0. Wow, I get 111. Because why? Because I put a little bit more work into this and made this oracle randomized. Okay, so you basically just get random results, but if you're somehow confused what your oracle was, you can basically look at your oracle type string. Like this oracle2 returns a string which just says the type of your oracle. Okay, nothing fancy. But the question is, like this circuit, there's nothing to it. We apply the same formula over and over and over again. The trick and the thing that you need to learn is how do you write these oracle functions? How do you write a function? How do you define a circuit that implements a given function fx? Alright, so let's see. Well, like I said earlier, to implement a constant function, you really don't need to do anything. But to implement a balance function, there is one thing that we can do. One trick. Okay, this trick was introduced in Qiskit textbooks page. I highly suggest you go and have a look at this page and just read it. They talk about the stuff that we talk about, but with more depth, and I think they're way more way better at it than I am. But let's go. So this DJ Oracle function, I also thought it was DJ Oracle, but turns out it's Deutsch-Jozsa for DJ. But anyways, for this DJ Oracle function is exactly the same as the one defined there. I just copy pasted it, and this Oracle2 function just randomly goes into one state, and we have the same recipe. This DJ Oracle produces a quantum gate, and we append this to our quantum gate. Okay, now look at our circuit again. I think this will make everything more clear for you. Okay, these are like the 0th, 1st, 3rd, 4th, and 5th indices, right? And we map these to 0, 0, 1, 1, 1, 0 to 0, 1 to 1, and etc. Because this range n plus 1 produces exactly the list 0, 1, 2, 3, 4, 5, right? Anyway, with these details out of the way, let's move on to balanced. For constant, again I said, there is nothing to it. You can just delete it and it will work the same. But for balanced, how will we do it? Okay, there are three parts to this problem. The first part is this middle, which is actually the key point that you need to understand. These are just like the little modifications that you can do. Okay, let me explain what this does in here. I'm sorry for not being able to write down. I just don't have this thing to write down my tablets or anything. My phone is 4-inch, so no luck with that too. So let me go over this. Okay, I claim, or they claim, that to implement a balance function, you can use this phase kickback effect. That is, since this is a minus state, you can just apply CNUTs from every qubit to, with like every qubit being the control qubit and target always being this ancilla. You can apply this control NOT gates and basically simulate the behavior of a balanced function, right? How do you do that? Okay, the state of our state just before it enters the oracle is this. It's like very long and very complicated. Also remember that I just got rid of the constants in front. It's a superposition state, right, of all possible bit strings. Now, when you apply a CNOT gate, okay, for example, look at this bit string. This bit string will not apply a CNOT to minus state because the control bits are all 0, right? So nothing will change in here. Now look at this bit string. In this bit string, again, nothing in here, but here it will apply one CNOT operator to minus state, okay? What does applying a CNOT operator does? It just applies a NOT gate to it. So this 0 minus 1 state becomes, this 1 becomes 0, so this is like minus 0, and this 0 becomes plus, and this becomes 1, so this is like plus 1. Well, can't write this simply as taking the minus out, 0 minus, that is minus 0, 0, 1, minus state, right? It just gets a minus sign in front. Well, you should expect this because plus and minus states are what? Eigenfunctions or eigenstates of X operator or NOT operator. So applying a NOT operator to plus state will just produce a plus 1 index eigenvalue and won't change the state. Similarly, for the minus state, you will just get a minus sign in front. Okay? So if you do this for each of the states, which is quite easy to do, you just look at if there are even number of ones, you just put a plus in front. If there are odd number of ones in the bit string, you just put a minus sign, right? So this is the final state you have, right after applying the oracle, right? Now before applying these Hadamard gates, I claim, which is a valid claim, that this superposition is actually Hadamard transformation of some bit string X, which I don't know. But I know that after applying these Hadamards, the bit string that is in here will be X, right? So that's a valuable information for me. Now, each sign in front, like Hadamard transformation definition, is this. So each sign in front is basically minus 1 to the power x dotted with z, which is being the binary dot formation. Now, from the information that we have in here, I can actually deduce what x is, right? Without even running the circuit. Now, let's see. From here, I can see that these don't give me any information, but this means that the last qubit, the last bit value of x bit string is just 1. And from here, I can get that the middle one is also 1. This doesn't give any information, but it gives a validation. That is, if you just multiply these two, what do you get? You get an even number. So this is plus. And this information, like this bit string, gives me that x, the first index of x, is also 1. So it says to me that this whole thing is actually the Hadamard transformation of 1, 1, 1. Right? So after measuring it, it was expected to get 1, 1, 1 mathematically. Now, what does this mean in terms of balanced functions? Remember the definition of this, like the Deutsch-Jozsa problem. Each state, in front of each state, what do you get? You get a minus 1 to the power fx, right? This is the eigenvalue of minus state when applied a UF operator, okay? So each state has an in front of it a minus 1 to the power fx, x being the bit string. So this balanced function, it basically means that it maps 0, 0, 0 to 0. It maps 0, 0, 1 to 1 because this is minus. It maps 0, 1, 0 to minus, right? And from phase kickback, what do we get? We get pluses and minuses all in front, right? Remember, what did I say? I said the C0 operator will get a minus sign in front if there are odd number of ones in the bit string, and you will get a even. If you have even number of ones in the bit string, you will get a plus sign. Well, there are 8 possible bit strings, and half of them have what? Odd number of ones, and other half has what? Even number of odds. So basically applying this C0 and making use of this phase kickback operation, what do you get? You kind of simulate the behavior of an balanced function, which does this mapping 0, 0 to 0, 0, 0, 1 to 1, etc. Okay, I think this should be clear. So this explains this part of our DJ oracle function. Okay, this is actually the critical part. Okay, now just as a quick review, what does these do? Okay, assume, for example, my circuit was as follows. Just before applying this X gates and C0 gates, I apply an X gate in front and an X gate in the end. Okay? I mean, before applying this X gate, everything will be the same. Why? Because applying X gate to the superposition, what will it do? Let's have a look. This is the superposition. I apply an X gate, it maps 0, 0, 0 to 0, 1, 0, 0, 0, 0, 1 to 0, 1, 1, etc. But all of them have the same sign. So it basically, if you don't, sorry about this, when you apply this X operator, it doesn't change anything because it's in a superposition of all possible states. But this is a special case because if this state had been 0, 1, 0, applying this X would change something because the signs in front of these weights, these states would be different. So you would need to apply this in order not to disturb whole situation. So we apply. Okay, that's what the first part of it does. Again, the middle part is I've explained it, and in the second part we again apply 0, 0, 0. So just before applying this state, this is the state that we have. There is nothing to it. This is just the same as before. There's nothing to it. So after applying the X gate, what will we do? The middle qubits of each bit, each qubit state will be what? Flipped. So this 0, 0, 0 becomes 0, 1, 0. 0, 0, 1 becomes 0, 1, 1, etc. Okay, it goes all the way. You just flip them. There's nothing to it. Now again, I will apply this Hadamard transformation argument, right? But let's look at the sign of 0, 0, 0. Well, it is minus, but its sign should be what? Let's have a look at the definition. Minus 1 to the power x dotted with z. Well, z, if z is 0, 0, this should be plus, right? So having a minus sign right in front of 0, 0 means this is basically global phase. So I can just take this minus in front and continue working with this. All right? Okay, I take this minus sign all the way up into front and just rearrange all the terms. What do I have? I have again 0, 0, 0, blah, 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 all these possible states. Again, I apply the same argument. I claim this is a Hadamard transformation of some bit string, this x. So for each z, I look at its sign and try to figure out what x is. And from here, I can figure out the third bit of x is 1. From here, I can figure out the second bit of x is 1. And from here, I can check. And from here, I check out that its x value is 1, 1, 1. Okay? So applying this x's actually doesn't change the measurement result that we have. Remember, it just adds as a global phase, but our measurement results don't change with these global phases. I hope everything is clear. So let's go back to DJ Oracle function. So what it does is basically it just generates some sort of a bit string, okay? And according to this bit string, for each 1 in this bit string, we apply X gates. For example, the bit string that I was talking about in here is 0, 1, 0. For each 1 in here, you just apply an X just before applying the CNUTs. Okay? You apply an X if this bit string's value is 1 at that point. Then you apply these CNUTs, and finally you apply the X's in the same place. Okay, let's, as a quick review, remember this doesn't change the value that you have. It just adds a global phase. So the whole this Oracle thing just basically simulates the behavior of a balanced function. Well, I hope you understood what it was about, but I strongly suggest that you actually go ahead and make these like calculations by yourself and try to figure out why the hell did we write these down? What the hell does phase kickback mean? Once you like get your hands a little bit dirty, you actually get the hang of it. I also highly suggest, again I will say it, to have a look at this Qiskit textbook. They talk about the problems way better than I do, and there are also more in-depth analysis of the situations. Well, as a homework, I guess I suggest you try to find another simulation of a balanced function. Maybe you can figure it out. Thank you for joining me.